An electrical explosion is a violent event resulting from the rapid release of energy due to an electrical fault. It's more than just a spark or a flash, it's a destructive phenomenon that can cause significant damage and injury. To understand the conditions necessary for an electrical explosion, we need to consider several key factors. Firstly, a high level of electrical current is essential. Without sufficient current flow, the energy available to create an explosion is limited. The amount of current required varies depending on the voltage, impedance of the circuit, and the nature of the fault. Secondly, a short circuit or a similar type of electrical fault is necessary. This fault provides a low resistance path for the current, allowing it to increase dramatically. A short circuit can occur due to insulation failure, accidental contact between conductors, or equipment malfunction. Thirdly, confinement plays a significant role. If the electrical fault occurs within an enclosed space, such as an electrical panel or a piece of equipment, the pressure generated by the arc and the rapidly expanding gases can build up, leading to an explosion. Without confinement, the energy is more likely to dissipate, reducing the severity of the event. Fourthly, the presence of flammable materials can exacerbate the situation. If flammable gases, liquids, or dusts are present in the vicinity of the electrical fault, they can ignite and contribute to the explosion. These materials can include solvents, fuels, or even combustible dust from manufacturing processes. Fifthly, voltage levels are important. Higher voltage systems generally have a greater potential for creating more energetic explosions. However, even low voltage systems can be dangerous if the available fault current is high enough. Sixthly, impedance in the circuit limits the amount of fault current that can flow. Higher impedance reduces the fault current, while lower impedance allows for a high fault current. Factors that contribute to low impedance include the proximity of the conductors, the size of the conductors, and the presence of grounding systems. Seventhly, the duration of the fault affects the amount of energy released. A longer fault duration means more energy is dissipated, increasing the potential for an explosion. Protective devices, such as circuit breakers and fuses, are designed to interrupt the fault current quickly and minimize the duration of the fault. Eighthly, the type of electrical equipment involved can influence the potential for an explosion. Certain types of equipment, such as transformers and switchgear, contain large amounts of energy and are more likely to be involved in electrical explosions. Ninthly, environmental conditions can play a role. Humidity, temperature, and atmospheric pressure can affect the conductivity of materials and the likelihood of arcing. Tenthly, the design and condition of the electrical system are critical. Systems that are poorly designed, improperly installed, or poorly maintained are more susceptible to electrical faults and explosions. In addition to these factors, it's important to understand the specific hazards associated with flying objects resulting from electrical explosions. These objects can include fragments of equipment, molten metal, and other debris that are ejected with considerable force. To mitigate these risks, several safety measures should be implemented. Firstly, proper personal protective equipment, or PPE, is essential. This includes arc-rated clothing, gloves, face shields, and other protective gear designed to withstand the heat and impact of an electrical explosion. The specific type of PPE required depends on the estimated incident energy level of the potential arc flash. Secondly, arc flash studies should be conducted to determine the potential incident energy levels at various points in the electrical system. These studies involve analyzing the system's configuration, voltage, fault current, and clearing times of protective devices. The results of the arc flash study are used to select the appropriate PPE and establish safe working distances. Thirdly, lockout-tagout procedures should be followed whenever working on or near energized electrical equipment. This involves de-energizing the equipment, verifying that it is de-energized, and applying locks and tags to prevent accidental re-energization. Fourthly, safe work practices should be implemented to minimize the risk of electrical faults. This includes using insulated tools, maintaining proper clearances, and avoiding contact with energized parts. Fifthly, regular inspections and maintenance of electrical equipment are crucial. This helps to identify and correct potential problems before they can lead to an electrical fault. Inspection should include checking for loose connections, damaged insulation, and other signs of wear and tear. Sixthly, grounding systems should be properly installed and maintained. A properly grounded system provides a low resistance path for fault current, helping to minimize the duration of the fault and reduce the risk of an explosion. Seventhly, overcurrent protection devices, such as circuit breakers and fuses, should be selected and coordinated to provide adequate protection against short circuits and overloads. These devices should be tested regularly to ensure that they are functioning properly. Eighthly, employees should be trained on the hazards of electrical explosions and the safety procedures that must be followed. Training should cover topics such as arc flash awareness, PPE requirements, lockout-tagout procedures, and safe work practices. Ninthly, engineering controls can be implemented to reduce the risk of electrical explosions. This includes installing arc-resistant switchgear, using remote racking systems, and implementing current-limiting devices. Tenthly, consider using non-conductive shields or barriers when working near potentially energized equipment. This adds another layer of physical protection. To further elaborate on specific scenarios within an electronics manufacturing facility, consider these additional points. In areas where there are high densities of electronic components, electrostatic discharge, or ESD, can create an unintended path for current leading to component failure, and in rare cases, if there is sufficient energy, can contribute to conditions leading to an electrical explosion. Strict ESD control programs, including grounded workstations, wrist straps, and conductive flooring, help minimize this risk. In the manufacturing environment, equipment such as reflow ovens and wave soldering machines rely on precise temperature control. Malfunctions in these systems can lead to overheating and potentially create thermal runaway conditions that, combined with electrical faults, can increase the likelihood of an explosion. Regular calibration and maintenance of temperature control systems are crucial. Furthermore, automated test equipment or ATE systems often operate at varying voltages and currents. If these systems are not properly designed and maintained, they can be prone to electrical faults, increasing the risk of explosions. Implementing robust safety interlocks and regular testing of ATE systems is essential. Many electronic manufacturing processes involve the use of flammable solvents for cleaning and degreasing. The presence of these solvents increases the risk of fire and explosion in the event of an electrical fault. Proper ventilation and storage of solvents are crucial. In addition, vapor monitoring systems and intrinsically safe equipment should be used in areas where flammable solvents are present. Power distribution within the facility must adhere to stringent electrical codes and standards. Improper wiring, inadequate grounding, and overloaded circuits can all contribute to the risk of electrical explosions. Regular inspections and upgrades of the electrical infrastructure are vital. Consider using arc flash relay systems. These systems detect the light from an arc flash and rapidly trip the circuit breaker, minimizing the energy released during an electrical fault. Arc flash relays provide faster protection than traditional overcurrent protection devices. Also consider current-limiting fuses, which are designed to quickly interrupt high fault currents, reducing the duration and energy of an arc flash. Current-limiting fuses can be used in conjunction with circuit breakers to provide enhanced protection. Remote racking systems allow operators to rack circuit breakers in and out from a safe distance, reducing their exposure to arc flash hazards. These systems are particularly useful for high-voltage equipment. High-resistance grounding systems limit the amount of fault current that can flow during a ground fault, reducing the risk of an arc flash. High-resistance grounding systems are commonly used in industrial facilities. Infrared thermography can be used to detect hotspots in electrical equipment, which can indicate loose connections, overloaded circuits, or other potential problems. Regular infrared thermography surveys can help identify and correct these problems before they lead to an electrical fault. Installing barriers and enclosures around electrical equipment can help to protect personnel from arc flash hazards. Barriers and enclosures should be designed to withstand the forces generated by an electrical explosion. Furthermore, conduct regular safety audits to identify potential electrical hazards and ensure that safety procedures are being followed. Safety audits should involve a review of the electrical system, equipment, and work practices. Review and update the facility's electrical safety program regularly to reflect changes in technology, regulations, and best practices. The electrical safety program should be comprehensive and address all aspects of electrical safety. Remember that preventing electrical explosions requires a multifaceted approach that includes engineering controls, administrative controls, and personal protective equipment. By implementing these measures, you can significantly reduce the risk of electrical explosions and protect workers from serious injury. Always consult with qualified electrical professionals to ensure that your electrical system is safe and compliant with applicable codes and standards. Remember, these are general guidelines, and a thorough risk assessment should be conducted by qualified professionals to determine the specific hazards and appropriate safety measures for your facility. Consider specific scenarios. For example, in robotic assembly lines, the robots themselves can present electrical hazards due to their complex wiring and high-voltage components. Regular inspections and maintenance of robotic systems, including checking for worn cables and loose connections, are essential. In cleanroom environments, static electricity can be a major concern. Static discharge can damage sensitive electronic components and create a risk of fire or explosion. Implementing static control measures, such as ionization systems and anti-static materials, is crucial. In areas where printed circuit boards are manufactured, chemical etching processes are often used. These processes can involve the use of corrosive chemicals that can damage electrical equipment and create a risk of electrical faults. Proper ventilation, containment, and spill control measures are essential. Power quality is also essential. Voltage sags, swells, and harmonic distortion can all contribute to equipment malfunction and increase the risk of electrical explosions. Implementing power quality monitoring and correction measures can help to improve the reliability of the electrical system. Additionally, consider using uninterruptible power supplies, or UPS systems, to provide backup power in the event of a power outage. UPS systems can prevent equipment shutdowns and reduce the risk of electrical faults. Also, surge protection devices, or SPD, can protect electrical equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at critical equipment locations. In areas where there are sensitive electronic components, electromagnetic interference, or EMI, can disrupt equipment operation and increase the risk of electrical faults. Shielding and filtering techniques can be used to reduce EMI. Regularly inspect flexible cords and extension cords for damage and replace them if necessary. Flexible cords and extension cords should be used only for temporary power and should not be used as a substitute for permanent wiring. Avoid overloading circuits by plugging too many devices into a single outlet or circuit. Overloaded circuits can overheat and cause a fire. Keep electrical panels and equipment rooms clean and free of debris. Dust, dirt, and other contaminants can accumulate and create a fire hazard. Establish a culture of safety within the facility by encouraging employees to report any electrical hazards they observe. Employees should be empowered to stop work if they believe there is a safety risk. It is also critical to maintain accurate and up-to-date electrical drawings and documentation. This information is essential for troubleshooting electrical problems and planning electrical work. Implement a system for tracking and managing electrical safety incidents. This information can be used to identify trends and improve the electrical safety program. Ensure that all electrical work is performed by qualified and licensed electricians. The electricians should be trained on the latest electrical codes and standards. Develop an emergency response plan for electrical incidents, including procedures for shutting off power, evacuating the area, and providing first aid. Conduct regular drills to ensure that employees are familiar with the emergency response plan. Communicate electrical safety information to all employees through posters, newsletters, and other channels. Make sure that employees are aware of the hazards of electricity and the safety precautions they should take. Consider using visual aids such as arc flash warning labels to alert employees to potential electrical hazards. Arc flash warning labels should be placed on electrical equipment that may be subject to arc flash hazards. Implement a system for managing and controlling access to electrical equipment rooms and areas. Access should be restricted to authorized personnel only. Review and update the electrical safety program at least annually to ensure that it is still effective and meets the needs of the facility. The review should involve input from employees, management, and safety professionals. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with qualified electrical professionals to ensure that your electrical system is safe and compliant with applicable codes and standards. By understanding the conditions necessary for an electrical explosion and implementing appropriate safety measures, you can significantly reduce the risk of these events and protect workers from serious injury.